In this video, we will discuss a few more problems on gravitational potential energy. We will show how to calculate gravitational potential energy, kinetic energy, the change in gravitational potential energy, the change in kinetic energy, and the applications of conservation of energy. Problem 1. Two colliding stars are separated by an initial distance of 1.5 times 10 to the power 9 meters. Each has a mass of 2 times 10 to the power 25 kg, so they are identical stars, and a radius of 1 times 10 to the power 4 meters. If they are initially at rest with respect to each other, how fast are they moving when they are about to collide? So let's sketch the initial state. So you have two stars separated by some distance, and let's call that distance that is given as 1.5 times 10 to the power 9 meters, and they are not moving. Now at the final state, what happens is that these two stars are colliding, so the surfaces are touching each other. Now that means the distance between them is 2 times the radius of each. And it's moving at some speed v. So each of them are colliding with the same speed v. And we want to know what v is. So the initial energy of the system consists of just the gravitational potential energy, and that is given by minus gravitational constant g times the product of masses, so that is m squared, over the distance, which is 1.5 times 10 to the power 9 meters. There is no kinetic energy because they are at rest initially. Note the mass of the stars are given, so each mass is 2 times 10 to the power 25 kg, and we know the value of g as 6.67 times 10 to the power minus 11 in SI units. Now the final energy of the system is again the kinetic energy of the system, which is half times mass times the square of the speed. Now there are two stars, so you have to multiply that by 2, plus the potential energy of the system, which is minus g, the product of the two masses, over, now the distance is 2 times the radius. The radius is known to be 1 times 10 to the power 4, so 2r is 2 times 10 to the power 4. So now we have to equate the initial energy to the final energy, because conservation of energy demands it, and we will have the following equation. The term on the left is the initial energy of the system, which is purely in the form of gravitational potential energy. The terms on the right consist of kinetic energy of the system. So this is the kinetic energy of the system, half times the mass times the square of the speed, and there are two stars, so times 2. So this mass here is that, and v squared is that. And this term here, the second term on the right, is the gravitational potential energy of the system while they are colliding. So you can see the distance between them is quite simply twice the radius. If the radius is 10 to the power 4 meters, so here twice that is 2 times 10 to the power 4 meters. We know what the value of g is, and we can therefore solve for the velocity or the speed when they are about to collide. And that's going to give you 2.6 times 10 to the power 5 meter per second. And that solves the problem. Problem 2. An object is dropped from 1500 kilometers above the surface of an asteroid, whose radius is 550 kilometers, and with a gravitational acceleration of 5 meters per second squared. With what speed will the object hit the asteroid? So let's sketch what's going on here. So the initial state, what you have is, so let's assume that is the asteroid, and the object is right here. Now the radius of the asteroid is 550 kilometers, and this distance here is 1500 kilometers, and the object is not moving, so it's being dropped from rest. So that means the initial energy of this object is just gravitational potential energy, and that's minus the gravitational constant times the product of the masses. This is the mass of the object and this is the mass of the asteroid, over this entire distance, which is 1500 plus 550, and let's convert it to meters by multiplying it by 1000. The final state of the system is when the object hits the asteroid with some speed v meter per second. So the final energy of this object would be kinetic energy plus the gravitational potential energy. So the kinetic energy of this object is half times its mass times the unknown speed that we are trying to compute, plus the gravitational potential energy is g, the gravitational constant, times the product of the masses, the mass of the object and the mass of the asteroid, over the distance. Now the distance is only 550 kilometers, and you can convert that into meter by multiplying it by 1000, because now the object is at the surface of the asteroid. Next, all we have to do is to compute the mass of the asteroid, because we are not given that. So we have to know what this capital M is. From our discussion on gravitation, on Newton's law of gravitation, we mentioned that the gravitational acceleration at the surface of, say, a planet is given by the gravitational constant times the mass of that planet or the object over the square of its radius. So we can use this to determine the mass m of this asteroid. Using the value of gravitational acceleration for the asteroid of 5 and the radius of 550 kilometers, we get the mass of the asteroid to be 2.3 times 10 to the power 22 kg. So from conservation of energy, we can equate these two terms, namely the initial energy and the final energy, and you see that the mass of the object will get cancelled, so it doesn't matter, we don't need to know. We know what g is, we have computed the mass of the asteroid, and we can compute the speed with which the object will hit the asteroid. And when you do that, you get the following for that speed: 2020 meter per second. And that solves the problem. Problem 3. The closest and the furthest distance between Earth and Sun while the Earth is orbiting the Sun is 1.47 times 10 to the power 11 meters and 1.52 times 10 to the power 11 meters respectively. Find the change in potential energy and the change in kinetic energy due to the variations in this distance. Now take mass of Earth to be 5.98 times 10 to the power 24 kg and mass of Sun to be 1.99 times 10 to the power 30 kg respectively. Let us compute the magnitude of the change in potential energy and the magnitude of the change in kinetic energy. So to compute the gravitational potential energy of the Earth-Sun system when the Earth is closest to the Sun, one need to compute the following expression. So minus g, the product of the two masses, mass of the Earth and the mass of the Sun, over the distance between them. So the closest distance is 1.47 times 10 to the power 11 meters. And that will give you minus 5.4 times 10 to the power 33 joules. Let's compute the potential energy of the system when the Earth is furthest from the Sun. And that's going to be, let's call it U sub F. And that's going to be minus G. The mass of this Earth is 5.98 times 10 to the power 24. Sun is 1.99 times 10 to the power 30. Now the furthest distance is 1.52 times 10 to the power 11. And that will give you 5.22 times 10 to the power 33 joules. With a minus, of course. And now we can compute the change in the potential energy. We can take, for example, since we're computing the magnitude, we can take UF minus UC, and that will give you 1.8 times 10 to the power 32 joules for the magnitude of the change in the potential energy of the system. What about the change in kinetic energy? The total energy is conserved, so the total energy does not change. We also know the change in the total energy is the change in potential energy plus the change in kinetic energy. So the change in kinetic energy is the change in the total energy, which is 0, minus the change in potential energy. So the magnitude of the change in kinetic energy is therefore is the same as the magnitude of the change in potential energy, which is 1.8 times 10 to the power 32 joules. And that solves the problem. Problem 4. Figure shows 4 10-gram masses located at the corners of a square. They're labeled as 1, 2, 3, and 4. X is 80 centimeters. That's the side of the square. If X is reduced from 220 centimeters from 80 centimeters, find the change in gravitational potential energy of the system. First, let's consider all possible pairs without counting them twice. So the potential energy of the system is given by first pair 1 and 2, so that's U1, 2. The second pair 1 and 3, so U1, 3. The third 1 and 4, so U1, 4. The fourth is 2, 3, so that is U2, 3, and then 2, 4, so that is U2, 4, and finally 3 and 4, so that's U3, 4. Note that the distance between masses 1, 2, 1, 4, 2, 3, and 3, 4 are all x, while the distance between 1, 3 and 2, 4, so they are diagonal distances, it's given by square root 2x using the Pythagoras theorem. So let's first compute the potential energy terms with x being the distance between the masses. And there are 4 of them. 1, 2, 1, 4, 2, 3, and 3, 4. So there are 4 of them, and each will be minus g, the product of masses, over x. Now the remaining ones would have the distance between the masses being square root 2 times x. So there are 2 of them, 2, minus g, product of masses, over square root 2x. Note x is reduced from 0.8 meters to 0.2 meters. So the change in potential energy would be the final potential energy when the distance between them is 20 centimeters minus the initial potential energy when the distance between them is 80 centimeters. Substituting mass, 10 grams converted into kg, and the value of the gravitational constant, we get the following for the change in potential energy. Minus 1.35 times 10 to the power minus 13 joules. And that solves the problem. Thank you for watching.